slides from ISIS. He's going to talk to us about the new LINAC tanks that are being built at ISIS. So I hand you over to Phil if he finds his talk.
Right, lucky me to get the last slot before lunch. My name is Phil Wise, as Dan Conley just said, mechanical engineer at ISIS. I'm going to give a very slight overview of what we do at ISIS and where my project fits in as quick as I can. Thankfully, John Walmsley's done half of that for me, so speed things up. Okay, so we're in Oxfordshire. It's quite a large site, a lot of history. On the back, on the other side, used to be Harwell, the Atomic Energy Research establishment. Zoning in to where we are on ISIS and what we look like. The grassy knoll, as I like to call it, is our synchrotron, and the target station 1, which is what John Wolsey was talking about when our protons hit the beam, is there, and the new addition is target station 2, which is roughly 10 years old now. There we go. Okay, so this is the slide. We start off, it's just slightly off there, with ion sources, have a LINAC accelerator. We've talked about synchrotron, protons, hit the target, and this is the bit that John Walmsley was talking about. That's very quick. Inside target station 1, inside target station 2, and onto my bit, the LINAC accelerator. So basically, there's 4 great big tanks, about 12 meters long, have a load of quadrupole drift tube magnets inside, which we use to accelerate the beam. So my simple brief 4 years ago was just replace one of the tanks, Phil. Can you look into replace one of the tanks? It's getting old. It's been vacuum cycling for a lot longer than it was designed to do, and it's now getting difficult to hold a vacuum. So it's got a lot more vacuum pumps on there than it was originally designed to do. So me being me, thought, well, how difficult can it be just to replace a tank? What I didn't realise is I had to find a test area, build a small amplifier, build quite a big amplifier, which is this one here, and all sorts of things. So basically, that's the old tank back in the day in the late 70s, early 80s. I think a lot of these drawings were made in 1976, which gives you an idea of how old these tanks are. And that was one great big structure, meter in diameter, 12 meters long, made out of mild steel and copper lined, because in accelerators we love everything to be copper lined. Back in the day, they used a process called explosive cladding, which was get some mild steel sheet, a thin bit of copper, have a little bit of gap, put some Acme Engineering gunpowder in the middle, light it, bang, and it sticks together. That's kind of explosive cladding. I looked into doing that because I quite fancied watching them make that. Unfortunately, it found out it'd be a lot cheaper if I just copper plate the structure instead. So there you go. That's inside. So what I've got here is a vacuum ports covered up so you don't drop nuts and bolts. And these are our drift tubes. So they're a copper cylinder, about 160 mil diameter. They're about, on tank 4, they're about 300 millimeters long. And the stem is about 500 mil, which it would be because it's a meter diameter tank. And we like them to be in the middle. Back in the day, technicians went down, led underneath, pushed these drift tubes up, tied them up the top, and then the alignment boys come along and leveled them all up to ridiculous tolerances. At the moment, we can't go in there because after 30 years of working, it's very active, far too active to go in. So that's the main driver for replacing the tank. If we lose 2 quadrupoles together, that means that ISIS goes down. So it's quite important that we have a contingency plan for the future. So start at the beginning. Thought, right, let's make a little test tank, see if we can get it right. Can't be that difficult. They did it back in the 70s. We've got a lot more advanced machines now. How silly was I? It proved very difficult to do. Lots of engineering challenges, but we are getting there. And that's what makes it enjoyable. So looking at the physics, the idea is I want to make a new tank that we can replace the drift tubes in the future. So I asked the physicist to say, can we put hatches in the side? How does that affect the RF and the fields and the operation of the tank? And the answer that came back was surprisingly very little That's not a bad idea. Phil, crack on with it. So that's what we've done. We've looked at how we get the drift tubes in and out the windows and how we can replace them in the future if we need to. There's a slide there of the Cockcroft-Walton generator. So what I had to do is not only make a tank, how difficult can that be? Big site, must be able to find a test area in Rutherford that we can do all this and see that it's right. That again proved difficult. Luckily, the Cockcroft generator, that room, that had all been stripped out and it was just a big empty room. So we thought, great, we can use that. And then I realized that we need to make the smaller amplifiers outside of the room, because when we're running the big amplifier, X-rays go everywhere and no one can go in there. So all sorts of shielding was designed. So there's stripping out the area. That's what it looked like. There's little bits of the aluminium floor left from where the Cockcroft-Walton generator was. I like this slide. I was having a terrible conversation on the phone with the controls and interlocks guy, and I said, wait a minute, I'll get my pad out. Did a quick, fag packet sketch, emailed it to him, and he went, Phil, why didn't you say that 10 minutes ago? So, pictures, I love pictures. This is inside the very first tank, because in ISIS, as the beam gets faster, the time gets faster, so we have about 50 drift tubes in the very first tank, and in the last tank we have about 25 drift tubes, just the way the physics is. I also like this slide is because when I did the drawings, the design for the tank, passed it over to the physicist, can you put it into your machines, let me know that I've got everything right? He said, no, you haven't got everything right, Phil. The diameter, it won't work at that diameter. And both of us, we couldn't understand. Alan jokingly said, oh, maybe they've put a lump of copper in the vessel to change the volume of the tank to make it work. After, I don't know, 6 months of looking quite hard, I managed to find some drawings of a thing called a bulk tuner. So it wasn't far off. That's a bit of copper in a T-shape to change the volume. So the throwaway question of, oh, maybe they just put some copper in there to change the volume was absolutely spot on. Unfortunately for me, those sets of drawings weren't linked to the main drawings. They were just somewhere else in the archive. So I was thinking about doing the similar thing for the next generation, but I haven't. Okay, so then basically we've got Dan's department, the iron source for our LINAC is in that hole. So I wanted to use this area when ISIS is running, which I couldn't, because again that gives off loads of radiation. So I've built a 600mm thick concrete wall around here so that we can use the area when ISIS is running. So to make the small amplifier, we thought, well, there's a bit of chalk there, there's a bit of room. Speak to our building estates, can we just, put 2 walls and a concrete floor in there? That'll do me, maybe a window and a door if we're lucky. And they went, yeah, sure, that'll be about £7 million, and 4 years later, but similar costs. So there it is in construction. There's my 2 walls and a door and a window, so I was quite happy in the end. And then the leak, loads of leak, winter come, loads of leaks on the roofs, because it's a flat roof, you've got to do the lot because you don't know where it's leaking. Generally, with fat roofs, it might be water coming in here, dribbles along, and then goes down into... So, yeah, nightmare with lots of high voltage going on inside the area. Again, just make a tank, Phil. I forgot about all this. But so this is making the test tank, the mild steel structure. That one seems to be leaking. It's not very watertight. There's doing vacuum tests to see that it holds the vacuum that we need before accepting manufacture. Again, a nice slide of making it. And then, yeah, no explosive cladding, copper plating. So it's nickel strike first on the top left-hand slide, just so that it got a key for the copper to work to. Putting these side hatches in proved a little bit difficult, because it's not just a matter of putting it into a bath, copper plating it, taken out. The size and the structure dictates whether you get thick copper and thin copper plating. So they had to come up with a design to put some anodes in here to try and get an even plating. And they managed to do that well, which was good. So I didn't mention that the test tank is 1/6. So it's 2 meters long but the same diameter. I like that slide. Electricians, tell I'm a mechanical engineer, can't you? What's going on there? And then Adrian Hooper probably won't like me very much for the next slide, but it does show the human side that we do on the project. It's all about the people and the skills. I gave this talk last week to the technicians, and I counted them up in the room while I was doing my speech, and there was 32 people, and I thought, blimey, that's just the technicians, and all of them had done something on this project. So the amount of people, the physicists, the electricians, design engineers, the manufacturers, it must be approaching 100 plus easy. Amount of people that I've roped in and tried to help me drive this project forward. Okay, so there's lots of bits. Diane, you probably recognise some of these parts here, and John. Daresbury Conley helped us out because manpower was just swamped at Rutherford to make the TH116 valve and platform, that whole area. I think from memory it's about £180,000 worth of machine components in there. So a big job, and thanks again to Daresbury for that. There's the test tank, managed to get it back looking nice and shiny. Looking inside, setting up on the rig, checking all vacuums again, and then starting to build it. And we're at the stage now where we've got the drift tubes inside in the tank, and with Mark Keeland and his team are wiring up the 116 and starting to get that commissioned before we can put RF power into the tank and see if I've done a half-decent job or not. So that's 4 years of my life, those slides. Thanks, Dan. A little chat in 4 years of my life. There's the next 4 years of my life. Still lots to do. We've got to commission the amplifiers. We've got to do a bead pool test. The physicists amongst you will understand that one. We've got to connect all the cooling. We want to run the tank for 6 weeks continuously to see if it breaks down with all the high voltages. How are we going to get the tank out and the new tank in? That's not going to be an easy thing. Then there's going to be, where do you put the old tank that's active? At the moment, we haven't really got room on site. But thankfully, we're not going to do it for 4 years. We're starting to talk about that and plan and work out how we're going to do it. And then make a 12-metre tank, put it in the test area, put some more beans into it for 6 weeks, see if it works. And if it does, then great. And then we'll look about putting it in our LINAC. So that's me, Dan. I'll try to get us back on time. So.